conference. Let's start.
You ready to do it?
Yes.
Okay, we passed out the blue sheets.
And David Black.
I'm sorry?
David Black.
Okay. So we have the blue sheets going around. Welcome to TSV area. We have the blue sheets going around, and David Black is our scribe, is that right? And do we have a Jabber scribe, or do we need one? Maybe not. I will join the Meet Echo and watch the Jabber from up here. Welcome. So it's been a. Is that okay? Is that good? It's been an interesting number one. We should start off with the note well, which has not changed recently, but that doesn't mean that the obligations have changed. I assume you guys will see that many times this week, but this is another one. We're in Monday afternoon session 3, and we want to do a little bit on TSV overview and status, and want to talk about a proposed research group that's probably people in TSV area will be interested in, at least some. Then we're going to have Michio Honda talk about network stacks integrating with NVMM Abstractions, and then we're going to have some open mic time. We always like to put up the slide for who's on the TSV area review team and how many reviews they've done. This has actually been a fairly light IETF cycle for reviews, and actually what's come to the ISG has been kind of light also, but like I said, we appreciate every one of them. And I have to say also that the reviews that we've been getting in the last couple of IETF cycles have had a lot of influence on how Mary and I fill out ballots, so we really appreciate that.
Yeah, big thank you.
We want to talk about our working groups. Do you want me to just go through and let you go through yours? Or? Sure. Okay, so DTN, I mean this is AD humor, but has been talking about custody transfer in the last IETF cycle, and that's been a pretty controversial topic, and they seem to have closed on it just in the last little bit. So I'm really impressed with that. IPPM is doing recharter discussions that would cover the adoption of in situ OAM. NFSV4 is doing recharter discussions after a really productive couple of IETF cycles. Thank you guys. Quick has the first implementation draft out at the hackathon yesterday. AD commented as well. TAPS has the last 2 working group drafts are past working group last call, so moving deep into implementation in API space. I have, TAPS was the first working group I chartered, and I have never been as happy about TAPS as I am now. Thank you all. TRAM is finishing up its final deliverables, and TSV working group, when you got 14 active working group drafts plus 17 active related drafts, some of which have been out for adoption calls. Wow.
So I will only mention the highlights, and one highlight is that AQM is basically closed. It's still listed here. I didn't push the button, but all documents are done. I'm waiting just for one single person to update the last document. Then also TCP Inc. has just submitted their main documents for publication, so they are kind of done. They have like some side documents they want to work on. Then also RMCAT is doing really good progress. There's like the first document is sent out for publication. I'm expecting more documents to come in. And then maybe one thing to mention is that there's still a discussion about proxy work in MPTCP. So if you're interested in that part.
Cool, thank you. Our documents published since IETF 98 has been, like I say, a little bit light, but that's not unique to transport. It's just been kind of a light IETF cycle since I think we just had a late IETF meeting and that kind of stuff. But we have gotten stuff through, and
Yeah, my understanding is mainly that it's mainly the AD's fault who are sitting on the document.
I've got one in AD. Anyway, but again, like I say, thank you all for the work you do. We did have one request for feedback from people, and I said I would put up a slide. This is the details on it, but there's a thread already started on the TSV area list. If you have something to add, please follow up there. And it's already, the people look like they've already received several helpful comments, so thank you for that. Anything else that we need to talk about?
No, we have first, so we also just usually announce interesting BoFs or research groups or whatever. So just before this meeting, there was a banana BoF. Do you have a slide on that? No. No. So I'm just telling you. So before this meeting, there was a banana BoF, so we're not reporting on that, and we don't announce it because it's already gone, but it has relation to transport, so maybe you should look at it if you're not aware of it. And then the other thing that might be interesting for transport is there's a proposed research group called path-aware networking, and Brian is sharing that and has, well, yeah, pitch it.
Yeah. So hi, I'm Brian Trammell. For those of you who don't know me, I'm also a co-chair of the proposed path-aware networking research group. So when we talk about path awareness, we're actually talking about it very much more from a transport standpoint than from sort of like lower layer standpoints. The thing that led us to put this together as a research group proposal was we've seen a whole lot of work recently, so BoFs as well as working groups, both in the internet and transport areas, where there's an element of path awareness, where the endpoints of a communication actually are participating more in sort of path selection or path control or getting more information about the path. So an obvious one of these is multipath TCP. There's other work in the internet area, so there's Spring, so for doing source routing with IPv6 segment routing. There's a giant long list of these. There's a lot of work sort of in SDN, which gives you enabling technologies for these things. So we're going to have an initial proposed research group meeting on Wednesday afternoon. We'll have a few presentations sort of from the near term to the long term sort of research goals in this area. And we'll be looking also from comments for transport people if we have the scope of this right, because it's something that we're looking to start off as a way to coordinate work on path awareness at these two layers, and research on path awareness at these two layers, and to bring that into the IETF. But we've taken a very much a transport focus on this because I'm a transport person, and an internet layer focus on this. And we're looking to see if there's sort of like comments on how that should be scoped. So please come by on Wednesday afternoon. Thank you very much.
While we're having the audio-visual moment here, I'd like to show this moment on the little USB adapter that goes with the slide advance clicker. It says not a USB drive. I don't know if this has been a problem in the past, but now we know.
So I can maybe tell you what we're doing here. So Michio will present some work. He presented some work on user space networking stacks a few TSV area meetings ago. And this is kind of some additional work in this space. And he asked us where to present it in the IETF, and we said we happily have here in the TSV area, but because it fits very well.
Do you have my slides?
As PDF? Or
PowerPoint, I also attached. I also attached PowerPoint.
yeah, but I don't have PowerPoint.
Just for
What's the
I
problem?
think, yeah, I think,
Yeah,
I think you can go, I think you can do that.
that should be fine.
Yeah, yeah, great, cool.
Yeah. Do you also want to use that thing? Yeah.
You just stick that in the USB.
No, you have to stick it
Yeah,
in.
plug it in first.
Oh yeah, this is so fancy Linux, so I don't think it works. So
It should be.
the-
It should be. Give it
No,
a-
I don't trust it. So
Okay, then you don't have to trust it,
just,
it's
I
true.
need some mics, I think.
There's
Should
a
I
mic.
use mic? Oh.
Then you have to tell us if you want the next slide.
All right, so good afternoon, everybody. And this is a little bit about the off-topic from transport layer because this is not particularly on some protocol. But given that these days I found networking API for transport layer is quite hot topic in transport area. So I decided to make presentation here. So basically all right, so basically I'm working on the new networking API for the world of non-volatile main memory, which is also known as persistent main memory. And this is joint work with the Giuseppe, Lars, and Doug Sandry in NetApp.
So you can stay in the box and tell us when you want the next slide, in that case.
I think it is there, right, it's fine. So maybe some people already know computer had main. So basically, what you learn about computer in school is basically you have a CPU, you have memory, whose data will go on when you plug your power cable out, and you have a disk to really save your data. But this world will want to change. So basically, the main memory becomes persistent, so a lot of work done. For example, Intel is announcing 3D cross point, which is like memory, but data stays there all the time, even after reboots. So there's a lot of such kind of non-volatile memory technologies, but the common characteristics is they are all byte addressable. You know that disk is not byte addressable, so you have to access physical disks by the block granularity, but persistent memory are byte addressable. And also they are very low latency compared to disks. So access latency for disks is basically the millisecond or hundreds of microseconds, even for SSDs. But non-volatile memory access latency become tens to thousands of nanoseconds. That is very, very low. So in the community of storage, there a lot of work is going. So in addition to research paper introduced here, there is a lot of work from industry. So the question is, given that this big change in the computing system, so what's the implications in networking? So let's review how today's storage and network stack looks like. So this picture is probably almost everybody knows, but having a little bit of new things. So you know that we have some I/O peripherals, we have disks and NIC, and for main memory, forget about NVMM now, but main memory you have, and on top of that, you have operating system stack, like memory management, network stack, including TCP/IP, and on top of that, you have socket APIs, which resembles file APIs for networking. And you also have file systems and application is running all on top of it. And when we plug non-volatile memory into the system, then currently the system looks like following. This is how Linux and Windows works today. So once you plug an NVMM device into main memory, then you can create file on top of it, because you can create file system on top of it. But once this file is M-mapped to user space application, user space directly access to data by load and store instructions. So if the data is disk, then you have to copy data onto buffer cache or memory once, then you can only access there. That's the difference. And the NVMM abstraction is the thin layer that enable this direct access to NVMM with mmap and creating file system on top of it. So when you move data from the NIC to the final destination or some file, then how today it works is the data comes to the NIC and goes up to the network stack, and application read that data, and application to memory copy that data from DRAM to non-volatile memory. So this is how the application data reception and data store looks like today. But this is actually a problem, and I'm not sure how this is problematic. So let's think about some simple transaction between client and the server. Basically, the client sends some data. Hey, I want to keep this data even after you crash. I want you to recover the data. So in this case, what we have to do is think about client. Client wants to save 1 kilobyte of data. How the thing looks like is client sends some data, and this data arrives at a NIC. Then the data is DMA'd into DRAM and processed by TCP and IP stack. Then the application reads this data and write to some file. After that, this is the important step. It has to issue some fsync, or the file is already nmapped. It has to issue the msync to make sure data is actually on the physical disk device, disk or SSD, whatever. Okay. After that, the server finally can acknowledge client, hey, your data is safe. I can recover your data even after I reboot. So this is an entire cycle. So when we have SSD or disk, this process took milliseconds. So out of that, the networking part, or in this picture, without the step number 4, it took only 40 nanoseconds, 40 microseconds. So there was nothing to do with networking, but once we replace the disk to non-volatile memory, this process takes only 42 microseconds in our measurement. So now the storage or saving data is very cheap, so the networking is actually a bottleneck. So we have to cut it. So this is a bit more synthetic measurement, and we did some tests like having one client and one server, and client sent continually the HTTP post to save 1 kilobyte of data, and the server takes the steps to store data persistently, and we changed the number of TCP connections. So let's please look only the white box or bars and the dark gray box and bars. So clearly, so left means throughput and right means latency, average latency. So clearly, compared to the networking only case, the storing data persistently causes a lot of bottleneck, a lot of problems. So reducing latency, reducing throughput a lot, and increasing latency a lot. So the goal of this work is reducing the performance degradation by persisting data. So actually, why this step is the problem is cache misses caused by memory copy. So usually the copying data so some people say copy is expensive, some people say copy is not expensive. So it depends on the situation. So for example, like this picture, so reading from network buffer and some kernel buffer to application buffer, but over and over. But if the application buffer stays in the same memory address or same location, it's actually pretty cheap, because the application buffer stays in the cache. when you store data, which means you have to persist this data and you have to keep data, and you can't overwrite this data. So actually, in storage perspective, the memory copy actually happens like this. So memory copy always happens to different destination. Oh, imagine that the destination file is already mapped to the application address space. So here is the result of where the cache misses happen in the system. So when we don't persist the data or we don't perform data copy from application buffer to this the log file, then the cache miss ratio is only 0.0004%. And most of the cache misses are happening in the network stack, but still only a little bit. But once we start saving data, persisting data, then a lot of cache misses happens in memory copy from application buffer to log file. So that's why we have to avoid data copy. So the one thing our integrated network stack and persistent memories abstraction is basically pretty simple. So the one important thing is we have to allocate packet buffers where NIC DMA is into the non-volatile main memory region, which is just a file created. And after that, we have to employ the zero copy API because we have seen that the copy is expensive. So the overall step looks like the data arrives at a NIC and the application reads that data after TCP/IP processing without zero copy. Then the application, since the memory is already persistent, so the application just somehow write metadata of particular buffer. For example, the packet buffer number 1, length, and offset. So I'm going to show you in more detail next. So this is how our system looks like. So basically we have the NIC ring. NIC ring is just the NIC hardware. And we have the file containing packet buffers, and we have a TCP/IP implementation. Okay. So think about the NIC is receiving the some request to be stored. In that case, first packet the NIC just received 4 packets. Each of them includes data or client request. So then the first packet is processed by TCP/IP input, and after that, the application reads this data. Okay? So application finds, oh, this data is important, or we have to store this data. Then the application opens another file to store metadata or some descriptor for that packet, and say, I want to say packet buffer 0, offset 100 bytes, and length 1,000 some bytes. Okay? But after that, there's one more step. So you know that today's NICs, this is a good thing. So today's NICs, when today's NICs DMS packet into memory, it only logically DMS into main memory because the data actually stays in last level cache. So when NIC receives packet, data is not actually on memory yet. So it is on the NICs, it is on CPU cache. So the application must explicitly flash the data and this metadata to actually persistently store data. Okay? So the next packet is also considered as data to be persisted. So the data is written back to the memory, and the metadata is also written back. So after that, let's think about the third packet was something, some data which is not to be stored. In that case, when application finds, oh, this data is not important, or some the key value store get. In that case, it simply skips this data to be written back to memory. And the final data was also considered as data to be persisted, so it's simply the flash data and metadata. So now we are going to show some result. And the good thing is that we implement that by extending netmap, and we don't need any kernel hacking to use this. It works from Linux kernel from 4.6 and above. So here's some result. So we compared this using some extended netmap API, and sorry, not extended netmap API, but extended TCP IP API, and using the method, data persisting method I explained before. So by avoiding memory copy, we can, the white bar is the not storing data at all. So theoretical, the limit of performance. And the white, light gray bars and boxes are the storing data by copying data, and dark gray one are our system. So we see quite a lot of performance improvement, and 10 to 88% throughput increase, and a lot of latency reduction. So using this API, so we have quite a lot of improvement. So there is some related work, but actually nobody thought about non-volatile main memory aware network stack, and nobody did some more TCP IP networking aware non-volatile main memory storage system. So here is the conclusion. So now with upcoming non-volatile memory or persistent memory, so networking APIs are now bottlenecks. So we must redesign networking API. So actually, you know that socket APIs today resembles disk API. So we can read and write, and we can send a file, but there is no official mmap for network stack officially. So we need some more memory-friendly APIs for TCP IP as well, because it becomes a bottleneck. And we have a lot of ongoing work, so we are brushing up APIs for better integration with netmap. And we are also currently the packet buffer must be a single file, but we found it is actually not very convenient because, for example, like a database application, it has the multiple files to keep it breaks or chunks file. So we have to support the packet buffer forming file system. And also we are building a lot of use case applications like key value stores and also some software switches as well. So, but in the end, so the proposing the network stack and some persistent memory, we are building these pictures like the architecture. So application, the database API application using netmap because it is a networking version of mmap to a file. But underneath, we have both network stack and file system, and we have non-volatile main memory and NIC. So I know that the transport working group are basically designing new transport API because to better utilize the rich transport protocol features, but the persistent memory are actually coming not only to data center servers, but also mobile devices. So how to utilize the non-volatile memory on the mobile devices is also a hot topic. So I think there is some value for transport community to think about this type of new computing device. Thank you very much.
Thank you. We have time for questions.
Jake Holland, did you try this with any encrypted traffic? And what's the sort of proposed solution?
So this doesn't touch the contents of data. So this doesn't concern contents about data. So it's completely
So it would remain
unrelated.
encrypted sort of on the non-volatile memory, and then you would...
because this is supposed to, in that case, the application is supposed to run as a server, which actually decrypts traffic.
Right. So you need to keep the key then?
Yeah, so this is basically end of system API.
Okay, thank you.
So,
Hi, Colin Perkins. I guess I should ask the obvious question, which is there any relation to what TAPS is doing?
so sorry again?
Is there any relation to what the TAPS working group is doing?
Yeah, so I found that the TAPS working group are defining the how to better utilize transport features. But I think that if we think about the API change is quite a big thing. So if we redesign APIs, I think we have to not only take into account some transport protocol features, but also some upcoming devices.
Right. Yes, and I mean, some of what TAPS is doing is looking at features and policies, but some of it is also thinking about what the API should look like.
Exactly. Yeah.
So it might be useful for you to come and talk to the TAPS group at some point.
Yeah.
Not that I want to bloat the scope of that group too big, but...
Yes, initially I tried to talk in the TAPS working group.
I mean, I think my point is if there's something obvious we should not be doing that's coming out of your work, we should know about that to make sure we don't accidentally do it.
Tommy Pauly, Apple. So yeah, thank you for sharing. This is really cool. Coming from working on some of the stuff in TAPS, at Apple, we're doing a lot of work on trying to define the API layers. Just recently, we deployed on our mobile devices the fact that underneath the higher level APIs, we are using kind of the shared memory model here with the user space stack, very similar to this. So it's interesting to see the applications here that you have with, because you have the different memory system, right? Because we're still running on traditional memory. So I'd be curious, yeah, how, like when you're comparing what you did, let's say with the kind of the NetMap API layer,
Yeah.
what considerations does the non-volatile memory add to that we wouldn't think of normally when we're doing NetMap on a traditional system? Are there things that to make sure we're flexible over everything that could come up in the future? What do we need to be careful about?
So the point is that, so where the transports, for example, network stack, the protocol stack, where the protocol stack exists, it really doesn't matter actually. Because basically the protocol stack is only part of the network stack. So like this, for example, you can bring the protocol stack with the network stack on top of NetMap API as well. So, but I mean, this model doesn't change anything what we propose actually. But for convenience, we are using kernel networks, kernel TCP/IP stack.
Right.
But as far as the memory management stays in the kernel or in NetMap, so it works.
Okay. Yeah, I think to the point of what would be useful to bring into TAPS, I imagine that's an area that we haven't gotten really into much is making sure that data path is optimal and stuff like that, and this probably seems quite related.
Mia Kulevin, so we had a side discussion which was related to the fact that we're thinking about using a message-based API in TAPS instead of a streaming API. And if I get it right, I think that would actually be favorable for your approach, right? Or do you think there's any big difference?
Yeah, so actually the major drawback of using NetMap API or kind of memory-based API for networking is some very extremely easy support of streaming. The streams is a bit difficult because application has to chunk data by themselves. Application has to segment data by themselves, but I think, the community or the world is moving into accepting this kind of thing. For example, Linux has KCM today, kernel connection multiplexer today, which enables message-based application can send traffic over, TCP application can send messages over message-based API, like send a message or something, to avoid the system call overhead. So I also want to hear what TAPS is doing for this kind of things.
Pierre Pfister, thank you very much for this very interesting presentation. I have two quite technical questions, not really related to networking at all. The first one is, did you consider using DPDK instead of NetMap?
So I haven't actually considered using DPDK because DPDK completely runs in user space, even device driver, you know. I actually don't like the perfect complete bypass approach, or I want to take the good part of the kernel. Like the kernel has good memory management system and very good protection and very good TCP IP stack. So.
Just in case you're interested, there is the VPP project. It's an open source project.
It's SPDK, right?
No, VPP, sorry. VPP, Vector Packet Processor. It's a networking stack in user space based on DPDK, and it has a TCP IP implementation as well. And my second question is...
it's DPK.
No, VPP, like Vector Packet Processor.
Okay. I'm asking later.
The fd.io project. And the other question is, would that approach work as well with PCI-based NVM?
Not really, no. No, because PCI-based NVM, I think it has buffer cache. So to access data, the data have to be brought from the actual physical device to main memory, like buffer cache, right?
Yeah, I think it works with DMA as well, but there is a...
okay, then it works.
No, but it's like maybe indirect DMA, like, I don't know, that was an actual question, so I don't know.
The limitation requirement is NIC must be able to DMA to that memory region.
Okay. Thank you very much again.
Hello, Philip Teasel, TU Berlin. I have a little evil question. So as we're seeing that a message-based APIs seems to be much better for most kind of networking traffic, and you say memory-based API is also much better. Do you see there's still room for some kind of stream-based API in the future, or is it just to go away sometime?
So I mean, once we have the message-based API, which is very, very fast, then of course we can add another layer to emulate that. So it's just, if we do stream API on, say, today's TCP, then we, of course, stream data, or we can write, say, 10 megabytes of data, but kernel is actually chunking data internally. I think we can also write 10 megabytes of data into UDP socket, I think. Then in that case, UDP layer segments this data into, IP fragments. So, anyway, we have at some point we have to segment some data. I think many protocol developers found segmenting by themselves is fine. I hope.
Huawei. So thanks for the presentation. So do you have any performance data of comparing this with the RDMA?
No.
Not yet. Any plan?
Yeah, so the RDMA is kind of bypassing everything.
Yes.
But in reality, we can't really do RDMA always because, for example, we need some congestion control, we need flow control, we need retransmission, or
So that's a trade-off, right? You trade off flexibility with performance, or?
Yeah. So at some point I should. It's just okay. My answer is just my lazy. I haven't done it yet.
Okay, thank you very much, Michio. Put it back into the... And that means we have actually 15 minutes left for open mic. So now you can complain. Or you can ask questions. Or you can even say how great we are.
But you only have 15 minutes to tell us how great we are.
Yeah, Bob, we can go get beer early.
I mean, that's good for the note taker.
And I think it would be fair for me, as long as nobody's running towards the microphone, to just say, I'm really happy with the work the TSV area overall is doing. It was, that was one of the big considerations for me being willing to serve a third term as your area director. We've gone from the first blow up that I had on after joining the on the ISG was the MPLS over UDP IETF last call. Some of you may remember that. And we've moved from that kind of relationship with the rest of the IETF to we are now getting requests for early transport review from a working group that's considering adopting a draft. It's like we can't do it much earlier. So, people are actually seeking us out for help now. And, it's not just the area directors who appreciate you, it's the rest of the IETF.
So also one last comment from my side, we didn't have any transport BoF this time. I think we're busy enough, but I'm actually about to close at least one working group, so there's also space for new ideas. So if you have anything to discuss, please come to us.
Absolutely.
Are you going to tell us which working group, or do we have to hold our breath and find out?
You saw that movie, right? And then there were 9.
No, it's AQM. It's basically dead, right? But
yeah,
if I think it's actually fun to press a button, maybe I press it more.
Yeah, and so we moved one of the chairs from AQM to TSVWG, so we know where to send new work in that space. It's also worth just me mentioning. My co-area director will be up for her position will be up for NOMCOM review this year. Please be considering your feedback because NOMCOM really appreciates feedback about the incumbents and about the needs of the area. Don't forget that part. They're supposed to be balancing, not like, do people think this person is doing a good job, but do they think that this person is the right person for what the area needs to be doing? So we're interested in those things as well.
Yeah, and please consider to put your name in.
And if you don't put your name in this year, I will be up for review the following year. And the only feedback that I got from NOMCOM, which they met with the people, the willing nominees, and said, this is the kind of feedback we got about you, was that serving a third term was a really big hurdle for them to get over. They said, there will not be a fourth. So if it takes you 6 months to figure out if you can do this, start soon. If it takes you 18 months to do this, that would be for me. Are we done? Cool. Thank you all, and we will see you in scenic Singapore.
Thank you.
Thank you. I think my blood pressure is about 130 if it was the TSV.